You are.
Yeah, off you go. Thank you.
Cool. Okay, so my talk today is about the challenge of trusting AI. My name is William Jones, and I am the AI and machine learning lead at Embecosm. So, obligatory slide on Embecosm before the meat of the talk. Embecosm is a tech consultancy focused on solving hard problems in computer science, particularly in open source. We are most known for our work in compilers and toolchains, but we also do work in embedded systems, operating systems, and of course AI and machine learning. And what I'm talking about today is sort of a overview of the AI specific challenges of trusting AI. So there's lots of challenges in trusting AI, sort of like security ones, implementation ones, but there's also some which are sort of specific to AI itself, which a lot of my colleagues have spoken about so far today. And to get started on this, I've sort of put up it's by no means a complete and perfect definition of what a trusted AI might do, but it's at least a definition to get us started on what we might want out of a trusted AI. And that is a system that is correct, explainable, fair, robust, transparent, and private. And what I'm going to do for the rest of the talk is talk through 5 examples in the real world of why this is really so difficult to achieve. The first one of these, one that we've touched on quite a lot so far, is fairness. How can we trust our AI to not be biased against any particular group or outcome? And this is actually really, really hard. And to give an example of how hard it is, I want to talk through a tricky situation Amazon seemed to have found themselves in a few years ago, sort of circa 2018. So Amazon hire a great deal of people, and hiring is a very, very resource-intensive process. Very reasonably, Amazon decided they wanted an AI to help them with their hiring, to sort of score their resumes for them, to take some of the work away. So what they did is sort of, I suspect, simplifying a great deal, is take a big stack of resumes they had collected it from their past employees and who they hired and didn't hire out of those, fed those into an AI and asked it to score future resumes based on these past ones. And the problem is that the AI that ended up being produced from this ended up being very, very biased. Among other things, it ended up being very, very gender biased. And ultimately, even despite the fact that Amazon have Amazon level resources and Amazon brains, and the problem of fairness in gender was sort of staring them straight in the face, they ended up abandoning this project because they couldn't solve this problem of bias, because it's a really difficult problem to solve. Ultimately, when they removed direct references to gender in their resumes, the AI simply learned to use indirect references because gender was such a strong predictor in their data set. Equally, when they started enforcing some measures of fairness on the data, on the AI just worked around it again because in their data set, gender was such a strong predictor. And yeah, this is the first issue in trusting AI I wanted to talk about, fairness, because making things fair in AI can be very, very difficult, even if you're Amazon. And even if the problem's staring you in the face, which it often won't be. In many real-world cases, we're going to be dealing with challenging situations in which the unfairness might not be so obvious. The second issue I wanted to talk about was privacy in AI, and there are a range of different things I could be referring to here. So specifically, what I wanted to talk about was training data leakage. So there is a problem with many naively implemented AI and machine learning algorithms where they can leak things about the data they were trained on. So you train your model on the data, you put the training data away, and yet an attacker can still learn potentially quite a lot about this training data just by starting from a little bit of context and access to your model. To real-world examples from this, a set of researchers working on a drug dosage data set. They took demographic data and genetic data from a set of individuals and used this to try and predict an appropriate dosage of the blood thinner warfarin. Very sensible thing to do. What they were able to show, though, is with access to this model, or access to querying this model, not necessarily the internals, they were able to, from a little bit of freely or fairly easily accessible demographic data about some of the individuals the model had been trained on, infer very accurately the genetic data of these same individuals. And this is obviously concerning. Demographic data is easy to get hold of, and genetic data is not, and it's very, very private. A more sort of visually compelling example is the one I have on this slide. This is an example of data leakage in face recognition. The setup here was that a AI had been trained to recognize faces. So you give it a picture of somebody's face and it tells you the identity. And again, what these researchers were able to do is, given an identity and given the ability to freely and repeatedly query this model, they were able to make a, I think most people would agree, quite accurate reconstruction of the identity of one of the people that the dataset had been trained on. And it's not a perfect reconstruction, but it's pretty damn good. It's certainly fairly reasonably identifiable. And this is the second challenge in that I'm talking about today of trusting AI, the challenge of privacy. And this is not an unsolvable problem, but it's a surprisingly difficult one. Fundamentally, in large data sets, you end up being able to identify individuals with a surprisingly small amount of data. The classic result being that you can identify 60% of Americans from gender, birth date, and zip code. You really do, from just a little bit of context, get the ability to infer quite a lot if care is not taken. The third thing I wanted to talk about was robustness, and particularly robustness to adversarial attacks. So we've touched on adversarial attacks a few times this afternoon, but to sort of be explicit about this, what we're talking about here is adversarial attacks, which are attacks on the data that goes into your AI. There's sort of two levels this can happen at. You can poison the data that the AI is trained on, or you can poison the data that the AI is inferring on. Obviously, if you can poison the data that the AI is trained on, sort of to some extent, all bets are off. You can do this in very subtle and insidious ways. It can be very difficult to detect, and it can obviously have catastrophic results. The example I want to talk through today, though, is not of this, which is sort of, in a sense, is almost obvious, but of the ability to come up with adversarial stimuli for AI applications without access to the training data, and just sort of with a broad understanding of how the model works, and frankly, some time. And this was some work McAfee did on hacking the Tesla AI in sort of 2019, 2020. And the goal here was to get the Tesla AI to misidentify speed limit signs by essentially sticking things on the signs so that they would be misclassified. And honestly, the things that were attached to the signs, and this sort of worked under realistic conditions, by the way, in the field. They're not overly obvious to a human observer. Looking from sort of left to right, like our left sign sort of looks a bit grubby. Maybe it's got some dirt on it to a human eye at first glance, but this causes the Tesla AI to very consistently misidentify the sign as 45, not 35. Our mental stimuli is a bit more colourful and obvious, but if you're not looking for adversarial stimuli and you saw this, you'd think something like, those damn kids are graffitiing my signs. You wouldn't think that your Tesla was about to misidentify the sign as 85 and not 35. And the most compelling example is, of course, on the right, with the addition of a little bit of sticky black tape, like duct tape. The speed limit sign is very consistently misidentified under realistic conditions as 85 and not 35. And this is very, very unobvious to the human eye. Like, if you look at that sign, you can sort of tell something's wrong. The 3 looks a bit funny, but that's quite, you looked at this at a glance, you really might not notice anything was wrong. And this is the third challenge of the 5 in trusting AI at the moment: adversarial attacks and adversarial stimuli. And steps can obviously be taken to mitigate this. You can train your AI to be robust to adversarial stimuli if you have particular adversarial stimuli in mind. If you can make the inner workings of your AI more obtuse, it's obviously much more difficult for people to engineer things like this. But fundamentally, it is difficult to stop people doing this thing full stop. And particularly, I think this is a compelling example because Tesla AI is trained on the most ridiculous amount of diverse data, and it still falls prey to attacks like this. The fourth thing I wanted to talk through was transparency and explainability. Again, this is something we've talked about a lot today, and it is, in a sense, I don't know, perhaps obvious. We have all these requirements of our AI. We want it to be correct. We want it to be trustworthy. all these things that we want. And if we don't understand how our AI is reasoning and how it's working and like how it's making decisions, it's very difficult for us to believe that it's going to be doing this. But this is a big challenge at the moment because in many fields, an explainable AI is not necessarily the best solution. The best solutions are often thoroughly unexplainable. Take, for example, the fields of natural language processing and computer vision. In these, neural network approaches are pretty dominant in many applications, but unfortunately, neural network approaches are fundamentally black box and very, very difficult for humans to reason about. And yeah, this is a big challenge at the moment, and it's also one that's not likely to go away. Fundamentally, there is in many senses a cost to making things human understandable. There's a sort of very real limit to the complexity and size of systems that humans can really feasibly reason about, and making your AI that is potentially reasoning about complex things fit things inside this box is not always easy. Yeah. Fifth and finally, I wanted to talk about the issue of uncertainty. And yeah, we have sort of touched on this a little bit before. And really the issue here is that in many AI applications, it's not good enough to just have an answer. We really, really need to understand the uncertainty and the risk associated with that answer so we can make sensible decisions about it. Self-driving cars has sort of been it's one obvious example of this. Finance is another. But the sort of real-world thing I want to consider here is in medicine. Consider the case I am an oncologist, so I treat cancer patients using an assistant AI. There's a range of different treatments that I can offer my patients, and there's a range of different risks that might happen to from these treatments. I could offer them sort of a routine biopsy, which is relatively low risk, or I could offer them extremely high risk and dangerous surgery if I deemed it necessary. If I'm using an AI assistant and it's to be of any use to me, I need to be able to understand how much it trusts how much it believes in the judgments it's making and how much I can trust it. And in particular, if I'm going to be recommending very, very dangerous high-risk surgery for a patient who needs it or is deemed to need it, I would want my AI to be extremely certain and to understand very strongly that this is a necessary step and that this is something that needs to be done. There is high certainty about it. And this is something that's very challenging to do at the moment. This is sort of my area of interest in particular. There's a range of techniques for tackling this problem. We could use Bayesian methods. There's several frequentist methods that can do similar things. But fundamentally, the computational tractability is the issue. There's no good methods that are also very, very fast methods that fit in with everything else. So having overviewed all of these things and been a bit doom and gloom about it all, I would really like to, I've labeled this the solution slide, and what I would really like to do is be able to tell you that there is sort of a wonderful solution to this all. And unfortunately, there's things we can do, but I can't tell you there's a good solution to everything. At the moment, solving these kind of problems is the hard bit. It really is. I mean, that's not to say we can't do anything. Sort of broadly, we can be knowledgeable about these things. We can be aware that these problems exist and that problems like them exist. That's probably the first and most important step. Obviously, we need to bring in relevant expertise to make sure we are tackling these problems in an appropriate way. That means both bringing in sort of AI expertise to sort of understand these problems at the appropriate algorithmic and implementation level, but also very much to bring in domain expertise to make sure that these problems are being solved in a way that is appropriate for the domain that they are being solved in. And finally, we need to potentially think and prepare to think about some very, very difficult questions. If we are being asked to make judgments, or if we are asking to make an AI that is fair and unbiased, we do potentially have to think about what fairness actually means, and we potentially have to make judgments about things at the level of equality of opportunity versus equality of outcome. Anyway, I've sort of tried to rush through this because this was going to be this was timed at 20 minutes, and I wanted some time for questions at the end. I hope I've not been too quick. But thank you for listening. Are there any questions?
Thank you, William. I'll just check the chat. I don't think there's anything in the chat. So I guess if we go back to your solutions slide, this is obviously a fast-moving area. Where's the? Have you got any specific domains where are areas where you would be looking to find solutions to these problems?
Well, I think the self-driving car one. Self-driving cars is an obvious one where, which we've discussed a little bit already, where we really would like solutions to some of these problems. Medicine, as I've said, is another one, and sort of less immediately scary, but also very, very important, is finance. We would really, really like to make sure, given how important the economy is to all of our well-being, that our financial weapons of mass destruction are not being disruptive and destructive, but are actually being useful to everybody.
So the question is more about how would people keep up to date with the potential solutions to these issues and the latest attacks and how to avoid those attacks, for example.
I think, well, attending talks like these is a splendid move, I think, for one. And other than that, like I am aware that the government publishes advice on these kind of things, and particularly a lot of the larger tech companies, IBM and Google, have taken quite an interest in making sure these areas are well covered and have been frequently publishing on these topics.
Okay, I don't think there's any more questions. So, for William, one's just come in. You mentioned assistive AI for medical applications. I don't know if you can read that. If AI is confidentially recommended the wrong treatment that leads to harm for patient, to what extent do you think each party should be legally or morally responsible?
Oh, what a splendid and difficult question. I think, well, I think it depends in what capacity the AI is helping to some degree, but I think ultimately in these situations, it's not entirely unreasonable to expect the doctor to make the final judgment about this kind of thing. The AI is ultimately a pattern recognition tool and can't reason like a human can, at least at the moment. And so the final judgment call does have to be made and does have to have the responsibility for the decision. But that's potentially a bit of a contentious opinion. So
okay,
and Jeremy's asked a nice question. Where do techniques like Bayesian inference and inductive logic programming stand as approaches to AI that address the issues they raise? I think these types of techniques, the Bayesian ones and the inductive logic programming ones, are really sort of in the almost in the fuzzy logic class of solutions to problems, in that they find probabilistic logical solutions to things, and to that extent, I think they are very, very good solutions to the transparency and explainability side of things. Problem size, pending obviously very large solutions, are hard to comprehend for anybody, and of course the uncertainty quantification thing. Bayesian methods really are about quantifying uncertainty and are sort of the gold standard in solving these kind of problems, though of course there are challenges in meeting them, in using them in every single application.
Perfect. I think that's very good timing. So thank you very much, William. And
thank you.
Thank you very much. And just to wrap up, so